In this video for Computer Science 9618, we're going to take a look at building a binary tree, but using object-oriented programming. So let's go ahead and get started. Now, building a binary tree using object-oriented programming could be a tested concept. Most likely, you'd be looking at a paper 4 question in order to do this. Now, object-oriented programming could net you more than enough points to pass paper 4, but when they tie object-oriented programming into a binary tree, can become a little more tricky. So I'm going to walk you through how to build one using object-oriented programming, how to print the tree out with its pointers, and how to print the values in ascending order using recursion. I'm also going to walk you through sections of the code so you can gain a firm understanding as to what is happening, because if you've watched any of my videos, it's not about knowing code, it's about understanding code. And that's so if you run into a slight error or error when you're programming it out, you're able to fix it. So let's take a look at our data and how our tree should look at the very end. So here's our data. Now it's going to be stored in a one-dimensional array, and I'm going to be using index 0. So that's where my first value or my root node is going to start. And here are going to be the values. So in index 0, I'm going to have 25. When I build my tree, I put that in the root node position. So there's my root node. Everything's going to be compared to 25 at first. My next value is 15. I look at my root node 25 and I ask myself, 15, is that less than or greater than 25? We know 15 is less than 25, so it's going to go to the left side of the tree to the left of 25. My next value is going to be 20. I ask myself, is 20 less than 25? Yes, it is, but I already have a node here, 15. So I ask myself, is 20 less than or greater than 15? We know 20 is greater than 15, so it's going to go to the right of 15. My next value is going to be 11. 11 is less than 25, so I'm going to the left side of the tree. There is already something here inside this node, so I compare it to 15. I know 11 is less than 15, so it's going to go to the left of 15. My next value is 28. 28 is greater than 25, so I know it's going to the right side of the tree. Currently, there's nothing on the right side, so that's going to be the first node on the right side of the tree. The next value is 31. 31 is greater than 25, but I already have a value there to the right side of 25. No problem. I take 31, I compare it to 28. I know 31 is greater than 28, so it's going to go to the right side of 28. And there's 31. My next value is 42. I compare 42 to 25. There's already something there. 42 to 28. There's already something here. 42 is greater than 31. There's nothing to the right side of 31. That's where I'm going to put it. My last value is going to be 4. I know 4 is less than 25. I know 4 is less than 15. And I know 4 is less than 11. So there is my final value. This is what our tree would look like if we were to draw it out in paper. Now you may be saying, well, 25, 15, 20, it doesn't follow the order like 25, 15, 28. 28 is way down here. What about the 20? The index of where these data values are being held in each of these nodes is just where it is stored. The pointers point to the next index of what's to the left and to the right of the tree. And you'll see that when we program it out. So let's take a look at the objects we're going to need, also known as our instances. So we're going to be using two classes, one for the binary tree. And here is the binary tree. It consists of the whole thing. And then we need a class for each node. These are all the nodes. The ones that have these circles with the values inside, those are the nodes. Now each node has a left pointer and a right pointer that points to the index. Now we want to follow the has a rule. When creating your attributes for your object, also known as an instance of a class, you follow the has a rule to get your attributes. So we ask ourselves, what does a binary tree have? A binary tree has a node or nodes, also has a root node, and the next available opening known as a free pointer. Now in our binary tree class, we're going to have those attributes. We're going to have an array of nodes. We're going to have our root node as well as the free pointer, so we know where we can put the next available set of data. But what does a node consist of? What does a node have? Well, each node has a left pointer, which we're going to abbreviate as left PTR, a right pointer, and the data of that node. Now, in our tree node class, we're going to have those attributes, left pointer, right pointer, and the data. Now, let's convert all this to code. So let's swing over to VB.net. Let's go ahead and create these classes and take a look at how to build and program out a binary tree using object-oriented programming. So now that we're in VB.net, we can go ahead and create our blueprints or our templates for each of the objects. The first one being the tree node. So I'm going to do public class tree node. And then we said, what does a tree node have? Well, it has data. And our data today is going to be an integer, but you could make it a string if you wanted to. We said it also has a left pointer. That's always going to be an integer, and a right pointer. That will also always be an integer. And the reason it's an integer is because it's pointing to the index of where the item that is less than the data and an item that is greater than the data. And we saw that on the binary tree. So these will always hold the index to an item that is less than for the left pointer, an item that is greater than that data, which is the right pointer. And it's pointing to the where it's stored in the index of the array, what index it's being stored at. Now, the next thing we need is our constructor. Now, when we construct a node, we know the data that we're going to have. So I'm going to do by val d as integer, and this will be for my data. As soon as I can spell integer correctly, there we go. So my data is going to be equivalent to the parameter d. But what about my left pointer? Well, my left pointer is always going to be equal to -1, and my right pointer, when I create this node, is also going to be equal to -1. But why is it -1? Well, there's a couple of reasons. First of all, I'm going to be using index 0 in my array. That means my null pointer needs to be -1. If I was starting at index 1 and skipping over index 0, 0 could be my null pointer. Because I'm going to include index 0, -1 is going to be my null pointer. The other reason it's -1 is because when I create a node, it doesn't have anything to the left or to the right of it. For example, when I create my root node, there's nothing to the left of the root node or to the right of the root node. When we put things into our binary tree by creating new nodes, we'll have a method that puts it in the right position according to the tree. How do we do that? We do that by updating the left and right pointers of the parent node. But we'll get to that in a few minutes. Because we'll be updating the right pointer and updating the left pointer, we need some set methods because our attributes are private. We cannot directly access them, so we use set methods to do that. So I'm going to do public sub, and I'm going to do set left pointer. And it does take a parameter. I'm going to do by val L as integer. And all I'm going to do is I'm going to set my left pointer equal to L. I'm going to do the same thing for my right pointer. So I'm going to do public sub, set right pointer. I'm going to do by val R as integer. And I'm just going to set my right pointer equal to R. We do not need a set method for our data because our constructor is going to handle when we set the data. But we do need to get our data. We do need to get the left pointer, and we also need to get the right pointer so we can see when we output our tree, we can get those things. That way we can make sure our tree was built correctly. Now, when you're using get methods, it's always going to be a public function. We're going to get data, no parameter. The return type is an integer, and all we do is we return data. We need another one for our left pointer. So I'm going to do, well, you want to do get left pointer. So we're going to get left pointer, no parameter. Return type is integer. And all I'm going to do is return that left pointer. And then one more, scroll down here a little bit. We're going to do another get method, public function, get right pointer. The return type is an integer, and I'm going to return the right pointer. And just like that, our tree node class is done. So the next thing we need to do is build our class or our template for our binary tree. Make sure you're outside your in class because we are creating a separate class, binary tree. And what does a binary tree have? Well, it has a set of nodes. We're going to create 8 nodes. You may be saying, why are you typing in 7? Don't forget, I am including index 0. When I count 0 to 7, that is 8. Now, that's not a string, that's not an integer. Those are actual tree node data types, and that's why we created that class earlier. Now, a binary tree also has a root node. That's going to be an integer, and it also has a free pointer, and that points to the next available index where we can store our data. Now, we are storing the data inside these tree nodes, and where we place it on the tree, we're going to be updating the parent pointer. So 25 is going to be our root node that has a left pointer of -1 and a right pointer of -1. When we add 15, we will be updating the node 15 with a left pointer of -1, the right pointer of -1. How do we place it in the tree correctly? By updating the parent node, which would be 25, we'll be updating its left pointer to 1, which points to the index of where that value can be found. And when we output the tree, you'll be able to see that. The next thing we need is our constructor. Now, our constructor is not going to take any parameters. All we're going to do is set the root node equal to -1. You may be saying, well, your root node really should start at 0. But what if my tree is empty and there's nothing there? Then my root node is -1. My free pointer is going to be set to 0, and that's because that's going to be the next available index. When I add my first node, I need to put that at index 0, which will represent my root node, and then my root node will move to 0. The next thing I need to do is I need to initialize all these indices inside my array of nodes. Because it is static and it's a predetermined fixed size, right now each index inside this array literally has a null value or the keyword nothing. This can cause a null exception error to be thrown, which means our program is going to crash. We don't want our program to crash. So what we want to do is we want to initialize it. Cambridge, 99 to 100% of the time, or if not all the time, they will have you initialize a array. So we're going to initialize it to -1, which is our representation of a null value. So we're going to do for I equals 0 to 7. Now, you don't have to do this to make your program work, but it will prevent any null exception errors to being thrown. Now, if you're using an array list or a list that is dynamic, you wouldn't have to do this at all because there is no predetermined sizes here. So we're just going to initialize it. We're going to do nodes I. And what are we doing here? We're creating a new tree node. And what are we doing? We're giving it the value of -1. This calls the constructor inside our tree node class, passes the value -1 to the data, but don't forget in our constructor, we also automatically assign the right and left pointer to -1 as well. So that's going to be it for setting up our binary tree class, but we have a couple methods that we need to add. Okay, the first method we need to do is an add node method. So we're going to do public sub add node. Now, this is part of the binary tree class, so make sure you're in the right spot. We're going to do by val, and we're going to create a new node. And what data type is that new node? That's the tree node data type, which means it's going to have data, a left pointer, and a right pointer. I need some variables. The first one is direction, because I need to know, am I going left or am I going right? I also need my current node. I need to know where I am currently, and I also need the parent node, because once I find out where I can place something inside the binary tree, I need to update that parent node, either its left pointer or its right pointer. Now, when we add a node for the very first time, we check our free pointer. If our free pointer is equal to 0, then we know we need to place the root node. That root node is going to be inside index 0. What am I putting inside index 0? That new node, because it's the first one being added. That means my root node is no longer -1, it's 0, and my free pointer gets updated by 1, because index 0 has already been used. And then, see here, we're missing our if statement here. There we go. So now my root node is no longer 0, or no longer -1. It is now 0, and then my free pointer gets updated by 1. Now that's one possibility. The other possibility is that our root pointer or our root node has already been placed. If that's the case, then my node's free pointer, whatever index is pointing to, that is the next available index, I'll be placing the new data into there. Now, this is not what places the new node into the binary tree. All this does is takes that data, the left pointer and right pointer, and puts it in the next index of the tree nodes that we have. It is a while loop that puts it into the binary tree. So what we're going to do is we're going to take our current node, and where do we want to start? We always want to start at the root node because it's not always going to be the root node. It will be the first time, but rather than having a bunch of if statements, by writing this one line of code, we can enter the loop and start at the root node and keep traversing the tree, either going left or right, looking for that -1. So we're going to do while current node is not equal to -1. Inside this loop, we're either going to go left or we're going to go right. Now, the first thing we need to do is take a look at that parent node, because if the current node is not -1, we're looking for the one that is -1. And if we find it, that means that is the parent node. So we're going to do parent node equals current node. Now we're going to have some if statements inside our loop that decides, do we need to go left or do we need to go right? So the first thing we need to do is check to see if we go left. So we're looking for the new node dot get data. If that new node, and we're taking the data, if it's less than where we currently are, our current node, then we know, and we got to use that get method, get data, then we know we need to go left. If I'm going left, I need to see the current node that I'm at is its left pointer -1. So I need to get that. So that means my current node, I need to check to see if it's -1, if my node's current node dot get left pointer. I need to see, is that equal to -1? If it is, then my direction is going to be left. That's one possibility. Another possibility, so we can do else if our new node dot get data is greater than our nodes. We're checking that current node, getting the data. If it's greater than, then we need to go right. So what I'm going to be doing is my current node isn't going to be equal to my left pointer. It's going to be equal to that right pointer. So I do nodes current node dot get right pointer. And it's very important that we make sure we get the right pointers here. Otherwise, when we go to output it, it's not going to work. And my direction is equal to right. So when I place 25, it's going to go inside index 0. When I place the next number, 15, it's going to take the current node, which is 0, because that's our root node. Our root node is 0. Well, while current node is not equal to -1, it's not because it's 0. Then we put our current node 0 into the parent node, which will be index 0, which is 25. Remember, I'm adding 15 first. Then I check to see if the data of this new node, 15, is less than 25. It is. So I get the left pointer, which is -1 for index 0 because we haven't updated it yet. That goes in the current node. My direction is left. When this loop goes back around, our current node is -1, which means we have found where it goes inside the binary tree. The next part of this code needs to go outside our loop. So let me put this in while here. Now we're still inside this outer for loop, and all I need to do is check if the direction is left or right. So if direction equals left, then what am I doing? Well, I'm taking the nodes. What node? The parent node that I found. And I'm setting its left pointer, which was -1, but I'm setting that left pointer to what? The free pointer. That will put it in the right spot. The other possibility is that we went right. If we go right, then our node's parent node, and we're going to set that right pointer. What are we setting that right pointer to? The free pointer. There we go. And just like that, we're done. Now, before we exit this method for the last time, because we just put something in the tree, we need to update that free pointer by 1. This is the add node method. That is the entire thing. When you're studying this or reviewing it, you want to break it into 3 sections. Here's section 1. The while loop is section 2. And the set of if statements that decide if we went left or right is section 3. With that, we're ready to print the tree, not print in ascending order. We'll do that in another method recursively, but the next thing we need to do is print the tree that shows the left pointer, the data, and the right pointer. All right, the next thing we need to do is public sub. I'm still inside my binary tree class, and all we're going to do is we're going to print the tree. It doesn't accept any parameters. The first thing I'm going to do is check my free pointer. You can also check your root node to see if it's equal to -1, but I'm going to check if my free pointer is equal to 0. If it is, then that means my tree is empty. So I'm just going to output a message, the tree is empty. If the free pointer is not 0, then that means I need to output everything, but I don't want to output -1 for everything. I only want to go to the objects that are actually inside my binary tree. So what I'm going to do is I'm going to do for I equals 0 to my free pointer -1. Because if my free pointer is pointing to index 3, that means I only need to go to index 2 because 0, 1, and 2 have something in it. And what I'm going to do is instead of having one giant console.write line, I'm going to do console.write. And what I'm going to do is I'm going to say left, and because that's going to show my left pointer, so I'm going to do nodes I dot get left pointer. So I'm just going to get that left pointer and we'll output that. Then I'm going to do another console.write. So this needs to be right, not right line. There we go. Otherwise, it's going to all be on a different line, a little harder to read. I'm going to put a space and I'm going to do my data. All right, there we go. Space and my data. And then all I'm going to do is nodes I, and I'm going to use that .get data method that we wrote earlier. Then console.write. And the last thing I need to output is that right pointer. So I'm going to do right and nodes I dot get right pointer. And when I get the right pointer, that will put everything. Now I don't want this all to go on one line. Like I don't want the next node to go on the same line, so I put in a console.write line. So just like that, this will output our binary tree. It'll output the left pointer, the data, followed by the right pointer. Remember, these pointers point to the index of where the value can be found. It doesn't point literally to the next part in the tree per se. It points to the next index. So we're going to take a look at our binary tree once we add our data and make sure that it matches exactly like it should. So let's take a look at outputting the tree recursively, and then we'll call each of those methods once we add those nodes. So now we're going to use a recursive sub. I'm going to call mine print ordered. And now, because it is recursive, we need to update the current node that we're at. So all we're going to do is we're going to check the left side of the tree. So nodes, the current node we're at, and we're going to start at index 0, and we'll do that when we call this. We're going to get that left pointer, and we're going to see if it's not equal to -1. If it's not equal to -1, then we know we need to keep going down the left side of the tree till we get to the bottom left. That means I need to call print ordered again. But what am I passing? What is going to be current? Well, that's going to be the node that I'm at, current, but what am I passing to it? Well, I need to get that left pointer. That's what I'm passing because I'm checking to see, is that left pointer equal to -1? Once it equals -1, what we can do is we can do console.write line, and all we're going to do, well, we're not going to output any quotes, what we're going to output is the current node that we're at, and what are we outputting? Well, we're not outputting the left pointer or the right pointer, we're outputting the data. So we need to know that data. Now, once we check the left side of the tree, we need to check the right side of the tree. So all we're going to do is we're going to do if nodes current, and we're going to, let's see here, make sure a dot goes in the right place. We want to get that right pointer, and we want to see if that's not equal to -1. If that's not equal to -1, then we need to go further down the right side of the tree. So all we're going to do is we're going to do print ordered, nodes, currents, and what are we passing this time? We're passing that right pointer. And just like that, this recursive method will output everything in ascending order. The last thing we need to do is jump down to our submain. We're going to create a new binary tree object. We're going to create some new nodes. Then we're going to print the tree, and then we're going to print all the data in order. So here's our submain. Rather than have you watch me type all this code in, repetitive code, I just went ahead and did it. So we're going to dim tree as a new binary tree. I thought tree was a wonderful object name for our binary tree. I can't call it binary tree because that is the name of the class. So I do tree.addNode. Remember, our add node is inside our binary tree class. How do I access that method? Through an object, and my object being tree. Now, when you add the node 25, remember our parameter was a tree node data type. If I take this out, it's going to say an integer can't be converted to a tree node data type. So I have to do new tree node 25, then 15, 20, 11, 28, 31, 42, and 4. Now, when we add the node, we should be updating its left and right pointers. So when we add 25, has a left pointer of -1, a right pointer of -1. When I add 15, it's less than 25. So we're looking for the parent node. How do we know what the parent node is? When its left pointer is -1. Once it's -1, I know where it goes because it currently doesn't have anything to the left of it. So that means it goes there. I need to update that parent node and erase the left pointer of -1 and reassign the free pointer 1, which is pointing to the next or the index that has the value that is less than that parent node. So when I add 28, for example, I check it against the root node 25. 25 has a right pointer of -1. Well, I have found out where it goes. I need to update that parent node 25, its right pointer, to point to the index where 28 is found, which means 25 should have a right pointer of index 0, 1, 2, 3, a right pointer of index 4. So when we run our code, we should see 25 with a left pointer of 1 and a right pointer of index 4. That's what this print tree does. It prints the left and right pointer as well as the data for each index. Then printing in order should print these values in ascending order. So let's go ahead, let's run our code. We'll check the ascending order first. 4, 11, 15, 20, 25, 28, 31, 42. We can see that it does put it in ascending order. Now, let's check our data in these pointers. Here's data 25. We said it should have a left pointer of 1 and a right pointer of index 4. And it does. It's not pointing to the actual value. It's pointing to the index of where the value can be found. 15 we know is to the left of 25. What is to the left of 15? Index 3. That means index 3 should be less than 15. Index 0, 1, 2, and index 3, which is 11. That is less than 15. Index 2 should be something greater than 15. 0, 1, 2. And we see 20 is inside index 2. This matches our binary tree that we created earlier. When I look at these data and check the pointers, and remember, the pointers point to the index number of where that data can be found, we can see it matches the binary tree. Hope you guys found this video helpful. If you did, please take a moment to give it a thumbs up and subscribe to help the channel grow, and we'll see you guys in the next programming video.